Hello, everyone. I'm Nate Mathews, and today I will be presenting our work on a new website encrypting attack named GANDALF. This work was led by Dr. Eun Oh from the University of Minnesota while she was still pursuing her PhD. In this project, she was joined by myself, Mohammad Saidur Rahman, and Dr. Wright of the Rochester Institute of Technology. This is alongside her advisor, Dr. Nicholas Hopper. Since many of you are likely already familiar with Tor, I'll try to keep this brief. Tor is a widely used anonymity system for protecting one's privacy and circumventing censorship. To defend its users, Tor incrementally creates a circuit containing a chain of 3 nodes that includes the guard, the middle, and the exit relay. This circuit is encrypted and extended 1 hop at a time, and consequently, no individual node has a complete path information. This means that each particular node is only aware of the nodes directly adjacent to itself. So if, for example, an attacker is monitoring the traffic between the user and the guard node, the attacker will know the identities of the user and the guard, but not the identity of the site that the user is visiting. In this way, user anonymity is preserved while browsing the internet on Tor. Unfortunately, there's a vantage point here that an attacker can exploit. In our attack scenario, the adversary knows the identity of the client, but not the website as it's protected by Tor. However, there was a leak of information within the metadata produced by the network traffic. This information is relatively distinct for each website, so an attacker can use this information to train a classifier to predict what website a user has visited. Such an adversary can carry out this attack by passively eavesdropping on the client in such a way that the client is completely unaware that the privacy of their communication has been compromised. And so this is what we call a website fingerprinting attack. Now, over the years, there have been many website fingerprinting attack proposals. Early attacks such as Kumul by Panchenko et al. And K-fingerprinting by Hayes et al. Process website traces into handcrafted features. These attacks use standard machine learning classifiers such as support vector machines, random forest, and the k-nearest neighbor algorithm to learn to predict websites using these features. In general, these works show that the features used to train the classifier are more important than the particular classification algorithm used. More recently, deep learning techniques such as stack denoising autoencoders and convolutional neural networks have begun to be applied to the field. These systems learn abstract features automatically from raw traffic data and have been shown to achieve superior performance. However, in order to feed these data-hungry networks, new larger datasets need to be collected. And so the current state-of-the-art attacks predominantly use convolutional models to achieve their high performance. Now, these deep learning techniques, however, created a new problem. The requirement for large data sets can be difficult to collect. Since websites change often, new data must be frequently recollected as old samples can become stale. And a model trained on stale data has been shown to experience severe performance degradation. To address this problem, recent research has focused on developing new low-data deep learning models that preserve the performance of deep learning without the demand of the many hundreds of instances per website. So Bott et al. Recently showed that an optimized ensemble ResNet model using dilated convolutions could learn much more efficiently than prior techniques, requiring only 100 samples to achieve state-of-the-art performance. Surinam et al. Instead identified that the discarding of the large stale data sets was wasteful and designed a model that could be pre-trained to learn to extract class-agnostic features using the stale data with the triplet loss training technique. Now, however, 100 samples, such as used by VAR CNN, is still quite a lot given the quickly changing nature of websites. And triplet fingerprinting, however, we see performs rather poorly in the more realistic open world setting. So our newest hack aims to improve along this line of research. When examining the current state of the fingerprinting domain, we realized that there was an additional data that is available to some adversaries, but was being left largely unused by the current techniques. This data is a vast amount of unlabeled website traffic data that is generated by the minute from the millions of users using Tor daily. In this case, it would be trivial for organizations such as your ISP, government entities, or even just operators of the Tor middle relay nodes to save a portion of this unlabeled traffic for future training. So in order to use this data, we need to develop a new training technique. To this end, we have developed a deep learning model that uses semi-supervised learning to train using a large repository of unlabeled data and requires only a small amount of labeled samples for the targeted classes. We call this the GANDALF attack. In order to do this, we have leveraged the power of generative adversarial networks. So in the next few slides, I'll go over the design of our new model, followed by a review of the experiments that we use to evaluate our system. So to understand our technique, we first need to briefly discuss generative adversarial networks, otherwise known as GANs. GANs were first introduced in 2014 by Goodfellow et al. To produce fake images. A GAN is a mini-max two-players game between a generator and a discriminator network. The goal of the generator network is to produce realistic images without access to real examples. The discriminator competes with the generator network to identify which samples were produced by the generator and which are the real examples. The generator uses information obtained from the discriminator to update its weights through every iteration. So in this way, the generator learns to produce images that fool the discriminator. The networks are carefully trained as a pair, such that neither is ever significantly better at its task than the other to avoid collapse. And in the computer vision domain, we see that this technique has been shown to be very successful at producing high-quality, high-resolution images that can sometimes fool even the discerning eye of a human. Now, this technique can be extended to perform semi-supervised learning. So in this model, the goal is to train a powerful discriminator that can perform effective multi-class classification. This is achieved by introducing class labels to some of the data used to train the discriminator. However, with a more powerful discriminator, the generator can be quickly outcompeted and may fail to produce realistic fake samples. So to address this, Saidur et al. Proposed the use of feature matching loss. This new loss function computes the difference between the middle layer feature outputs of the discriminator for the real and the fake data. This loss is then a measure of how statistically similar the features are for the real and the fake samples. In this way, the generator is trained explicitly to produce samples that closely resemble the real features that the discriminator is using to classify the labeled data. Now, on the other hand, the discriminator must now learn to perform two functions. First, it must learn to classify the labeled data with high accuracy. And second, it must learn robust features that allow it to separate the real unlabeled data from the fake data produced by the generator. The point of this is that the discriminator will learn how to extract features of the unlabeled data from the unlabeled data because it needs them to distinguish between real and fake samples. So in this way, the unlabeled and generated samples are used to bootstrap the feature learning process, allowing the model to learn robust features to classify labeled data. Now, when adapting this construction to our website fingerprinting domain, there are some differences that must be considered. In the computer vision domain, Saidur sampled examples from the same MNIST distribution to fill both their unlabeled and labeled datasets. However, in our website fingerprinting problem, the unlabeled data is instead sampled from a different data distribution than the labeled samples, as one will contain samples from many unknown classes, whereas the other contains samples from only a handful of targeted classes. So that's to say that there is little to no overlap of the classes present in our labeled and unlabeled data sets. So in our experience, we found that the distance between our labeled and unlabeled samples are generally much greater than that of the distances between Saidu's data sets. And this may somewhat limit the effectiveness of this technique within our website fingerprinting domain. So we built our GANDALF model on top of the model used by Saidur et al. However, there was required several architectural changes to adapt to our domain. So first, we converted the model to operate on one-dimensional data and expanded the depth of the networks to be much deeper. To address the instability that the deeper networks caused, we added additional regularization in the form of dropout and batch normalization layers. Additionally, we modified how the feature matching loss was computed to instead use the mean squared distance between the feature real and the fake samples. Using the mean squared distance more severely punishes large errors in the generator, which we found empirically improves the performance of the model when operating on website traffic. We also adjusted many hyperparameters using a grid space search, for which the full details of can be found in our paper. So up next, we'll be reviewing the results of our evaluations against GANDALF. Website fingerprinting experiments are performed in two scenarios, closed world and open world setting. These scenarios describe what restrictions have been put on the experiment. In the closed world experiments, the classification model is only given traffic from a small set of monitored websites. This experiment type does not accurately represent the real world performance, but is often used to benchmark models and techniques against one another. On the other hand, the open world setting makes the experiment more realistic by including samples from a large set of sites that were unseen by the model during training. This unmonitored set of sites represents traffic from the many millions of sites that the adversary is not interested in identifying. The open world scenario, as such, is a more difficult task than the closed world scenario, and is a better indicator of the real world performance. And we use precision and recall metrics in this setting. So in this paper, we also performed our evaluations under two different additional perspectives. In the first, what we call website fingerprinting for index pages, we use the large data sets collected by Saidur et al. And Rahman et al. In this scenario, each website is represented by samples produced from visiting its index page, and only its index page. This represents the way website fingerprinting has been performed throughout much of the previous literature. Now, in addition to this, we also run experiments where each website is instead represented using samples produced through visiting a subset of the many subpages available on that site. This type of website fingerprinting was first examined by Panchenko et al. However, we have collected a new, more recent data set and are the first to evaluate many of the deep learning methods under this scenario. This new subpage data set contains samples from 25 websites. Each website is represented by 96 unique subpages, with each subpage having 39 individual samples. This produces a total of approximately 93,000 samples for the new data set. So we will first look at the performance of the models in the closed world index page setting. Each model is trained using a number of samples per website that varies from 5 to 90 samples in the experiments. In this setting, we find that when the number of training samples is 10, GANDALF matches the performance of triplet fingerprinting. When the number of samples increases, GANDALF outperforms triplet fingerprinting, but is itself in turn outperformed by VAR-CNN. Now, when we switch to the open world setting, we find that GANDALF performs much more admirably, despite its somewhat underwhelming closed world performance. Here we have plotted the precision and recall of KFP, triplet fingerprinting, in GANDALF. GANDALF was plotted when tested at 3 different sizes of the background set, while KFP and triplet fingerprinting were both evaluated using a background set size of 360,000. The KFP and triplet fingerprinting plots can be directly compared to the dark blue plot of GANDALF. We see that GANDALF achieves much higher recall at comparable levels of precision than the other two attacks. It is, however, interesting to note that KFP achieves the highest maximum precision, albeit with a much lower recall than GANDALF. So up next, we'll take a look at the performance against the subpage fingerprinting dataset. So first, all across the board, we see that the performance is much reduced. This is likely due to the fact that the intra-class variance is much higher here than in the index page only dataset. We see that GANDALF marginally outperforms the other models when the number of training samples are 50 or more. However, is beat by KFP when the training instance count is very low. Next, we'll look at the open world performance in the same setting. In this situation, we find that KFP significantly outperforms GANDALF, achieving both higher maximum precision and recall when evaluated with a background set of 70,000. The effectiveness of KFP in this setting is likely due to the high difficulty of learning good features with few training samples. KFP uses handcrafted features, so avoids many of these problems. Now, furthermore, we also examine the impact of circuit speed and congestion on our model. In these experiments, we separate the data from Saidur et al. By the circuits they were collected on. First, we examine the performance of GANDALF when the model is trained on one set of circuits and tested on another, while we also vary the number of unique circuits used for training. Then we separate circuits by their speed, Samples that completed in the top 25th percentile were labeled as fast, whereas samples within the lower 25th percentile are labeled as slow. We then trained on one set and then tested on the other. Now, in both of these experiments, we found that the model does not perform significantly differently, indicating that the effect of the circuit characteristics on the traffic fingerprintability is minimal. Now, finally, we evaluated the effect of using different data sets as the unlabeled data to train our GANDALF model. We select data sets that vary in size, network conditions, and collection time to evaluate their effects on the performance of our model. We saw that generally the model performed better with the unlabeled data of a larger variety, yet overall the effect on performance is small. So now, in conclusion, we have presented a new website fingerprinting attack for the low data setting and performed extensive evaluations of several models under the setting. We found that semi-supervised learning with GANDALF offered strong performance in the open world setting and competitive performance in the closed world by taking advantage of the previously untapped unlabeled data. Using our newly collected subpage dataset, we have found that fingerprinting a website from the broader perspective of its many subpages is a particularly difficult task, especially for deep learning models. When examined in the low data setting, we were surprised to find that the KFP model outperformed all the deep learning models using handcrafted features under the subpage setting. And so finally, there exists a number of interesting directions that could be built on this research in the future. The semi-supervised learning structure of GANDALF could be extended using a conditional generator. This may allow the generator to produce more convincing fake samples that lead to the discriminator finding more robust features. Additionally, unlabeled data may be taken advantage of by assigning fuzzy labels and could be used to augment the size of the label data set, although it's yet to be seen how effective these additional techniques would be. Now, we also believe that there is much room for improvement in the combination of many previous techniques to better enhance the classification system by taking advantage of many data sources, such as the stale data as done in triplet fingerprinting and unlabeled data in our attack. And now finally, our performance in the subpage setting has shown that there's still much work still to be done in improving the performance of fingerprinting websites more broadly using their subpages. And so with that, you can find our code for the project on our GitHub, and you're welcome to contact any of us regarding the project through our emails as listed on the slide. And so, are there any questions?